Thank you for Professor Project. It was really an exciting presentation. I'm sure that there's people in the audience who would like to ask something about the work that he did and the experience that he made. So there's plenty of time. I think Professor will stay with us this morning, so if during the coffee break you can have the chance to ask him. The second presentation is from Dr. Keskin. I had the chance to listen to his presentation in UK time ago, and I found it quite interesting. You see, Dr. Keskin graduated in aerospace engineering with focus on turbomachinery design at the Berlin University of Technology in Germany, and then he had a PhD in mechanical engineering with a focus on process automation and design optimization at Cottbus University, again in Germany. He started working for Rolls-Royce some 15 years ago, and I would say that the title of his presentation goes exactly on the topic of our conference, since the title is The Use of Simulation in the Past, Today, and in the Future. Thank you, Dr. Keskin, to join this meeting.
Thank you very much. Thank you very much. Good morning, everybody. Good morning, ladies and gentlemen. I would like to start with some apologies. So that's the first time for me to attend this conference, so I missed the first 31st event, sorry for that. But it's an honor for me to be here and to present a few slides and share with you my thoughts about simulation. As already said in the introduction, so I'm doing simulation or 15, 16 years in the industry. So the simulation industry is slightly different to the academia part, but we obviously need to bring the things together. So my presentation is entitled Simulation, so what we've done in the past, where we are today and in the future. That's my view and the view of the company that I'm representing here. Just to clarify, I'm not driving a Rolls-Royce car, so I'm from the Rolls-Royce Aerospace division. So turbomachinery design is my focus. That's the reason why you see one of our latest products on the screen. Okay, let's start. Talking about simulation, I think to start off with, I thought it would be good to calibrate ourselves to make sure that we talk about the same simulation. So some of you might remember this scene roughly 14 years ago. My heart was supporting the red team, my brain was supporting the yellow team. Yeah, not good. But that was a different type of simulation. That's not what I'm going to talk about. So what about this one? Sorry for the poor quality, but I think it looks much more exciting. And in fact, it's a computer game, as you might have spotted already. And the key message here is, it looks fantastic, and it's really entertaining, etc. However, it only looks fantastic. So believe me, the equations solved in that computer game are not the equations that we would usually solve when we try to solve engineering problems very precisely. So, okay, let's start with the content of my presentation. So first of all, from an industrial point of view, simulation is important. Yes, we know that, but what is the business case? So why are we doing it? And why do we believe in simulation? And why do we believe that simulation is even more important in the future? Just a brief history. I don't want to go back that far, but I'm happy to share with you a few slides on that. Where we are today, that's my view, based on what we do in the company with 18,000 engineers, and roughly 10,000 of those 18,000 are using simulation data or simulation environments, and based on the knowledge I gathered by attending conferences, AIAA, ASME, Turbo Expo, etc. And what might be the future? Okay. So why is simulation important today? From an industrial point of view, we have a lot of challenges, and the biggest challenge is that we have a lot of requirements coming from our customers, which are the airframers, the big customers, or Boeing, Airbus, who come to us and ask for a design with a lot of constraints. Okay, and the only way to meet those requirements, to create a solution, is by doing a lot of simulations very early in the design process. The other point is, and I think we are not the only industry with that problem or that challenge here, is that we are trying to create more and more products and develop more and more products in parallel. Without necessarily increasing the workforce. So the only way to do that and still keep up the quality of the products is basically by starting to believe more in the abilities and capabilities of computer software. That's an important point for us. Obviously, we want to make business, we want to make money with it. Okay, so we need to, we are using simulation not just to design the product, also to support the product throughout its life cycle. And the last one is not only that the customer wants good solutions, good quality products, and we are trying to serve more customers, we also have been given less time to create a design. So a typical time for create an aero engine in the past was roughly 5 years. Today we are probably at 3.5 years, and believe me or not, the goal is to reduce that down to 18 months. Okay. And how can we do that without using simulation? Okay, one quote I like from William H. Press. I don't know how many of you still know the numerical recipes, which were on my desk for many years, with a lot of a good collection of numerical algorithms when I was doing real work and coding Fortran and stuff like that. So I truly believe in that quote, that simulation is really supporting that idea, and that's 1998. Okay, that's quite a lot of big time, roughly 20 years now back, and I truly believe in that. Okay, so first of all, if my seniors come to me and say, well, why do we do all the simulation? Why are we not doing testing, etc.? Then there are a few good reasons, and I'm not against testing, but I can come to that in a second. But generally speaking, simulation is, in most cases, much cheaper and much safer than doing tests. It can be even more realistic, which sounds, well, some people have a problem with that statement, but yes, I mean, our products, they fly 10, 11, 12 kilometers in the air. I can't test the product always in flight. I do tests on the ground, so I must do a lot of assumptions on Reynolds number, Mach numbers, and things like that. So, but with a computer model, I can change boundary conditions easily. So it can be really more realistic. And it can be conducted faster. That's true for small or low fidelity simulation, but for high fidelity simulation, they can easily take weeks or months, and I will bring up an example later on that. But in generally speaking, they are faster. Okay, Let's see. Okay, just a brief history. So I nicked that from a colleague of mine who retired a few weeks ago. He's the guy at the front. That's the Rolls-Royce office roughly 30 years ago. Okay, so impressive size monitors. Yeah, that was the depth. The distance that you need to accelerate the electrons, yeah, on the screen. But that was roughly 25, 30 years ago. That's not Rolls-Royce anymore, and I guess a lot of companies, industry companies in that area look probably like this one. This is from Google, because I was not allowed to share Rolls-Royce office, but I can tell you that our offices today look very similar. With a lot of laptops and things like that, we call that agile working, and we have dev cells and whatever, but that's how it looks like today. So why do I bring it up? Because not only the tools, the software, the computers are changing, the environment is changing as well. Okay, so if I would ask my boys what they think engineering is about, they would probably point to this picture rather than the previous one. But that's just to bring it into context. So, environment is changing, software is changing, everything is changing. So let's come a little bit more to the technical part. Here, I've got two examples here on the top left. This is an airfoil, a fan blade. So if you look into an air engine front, that's the airfoil. Just to bring you up that one, that's meshed with just few hundreds of nodes on the top left. Today we use millions of nodes per blade row. Okay, so there is a significant increase in mesh size, in level of detail on the geometry side, on the boundary conditions, etc. The bottom left is a very simplistic Nastran model with, again, few hundreds, I think not even 1,000 nodes. Today we are running simulations which have got a design of freedom of 200 million, 300 million. Okay, thermomechanical models, that's completely different thing. Okay, and believe me or not, you can get much more results out of the bottom right. Although the bottom left is still something that we do, obviously with much more mesh points today. Okay, do you know what that is? I'll give you a hint. So that's the development of an iPhone. Speed measured in gigaflops over the last few years. That's not even 10 years. So why do I bring that up? Just to show you that the compute power that you've got in your pocket, my iPhone is somewhere over there, is today much higher than the NASA's computer back 50, 60 years ago when they sent a man to the moon. So that's something we need to remember, yeah? And the speed of hardware, of computer power, is increasing significantly. I've not put the iPhone 7 on there. Would go through the roof, so 350 gigaflops roughly. Okay, so this is an acceleration just of a phone, factor than 100, roughly 150 and more, if you take the iPhone 7 into account as well. And that over a period of just 6-7 years. Okay, so if we look at the compute power that we have in the world, that's a chart which I'm using quite frequently just to explain. So it's basically, you see there are three curves. One is the top curve is the HPC, high performance computing capacity or capability in the world. Today's biggest computer, I think, sits somewhere in China with 3 million cores. So you can see how the compute power increases. That's the top of the 500. The light blue one is the 500th computer, and in an average, that's the red curve. You can imagine that the average lies towards 300, 350 rather than to the big one. There are just few of those in the world. So, but what you can see is that we have an increase of compute power and capability of a factor of 10 every 4 years. That's roughly aligned with Moore's law, but that shows us, okay, our computers get quicker, okay? But not only that, computers also get cheaper. Okay, and that's obviously, both of them are really beneficial in terms of a business case. Okay, so that's basically the money that you pay, and in this case US dollars per gigaflops over the last year. So this is all data that we collected ourselves. Okay, but that also shows that compute power gets cheaper. And you know that when you go and buy a laptop, you roughly pay the same as last year, roughly the same as 5 years ago, but what you get is much faster, probably more USB ports and better graphics card, whatever. So basically you pay them the same, but you get something faster. And in some areas even it is cheaper. So that's all great for the business case, but what do we need for simulation and to support simulation better in this future? So that one thing was the hardware. The other one is the software itself, so operating systems and things like that. And then the numerical methods, the algorithms. Okay, when we solve a finite element problem, computation fluid dynamics problem, etc., the algorithm needs to be faster and need to be better. So it's a combination of hardware, the software, the operating system, the algorithms, plus automation. And automation is something I truly believe in, is basically to release the engineer from non-value added task and bring them back to the engineering. So if I go around in my company and see people copying data from one Excel spreadsheet in another Excel spreadsheet, this is clearly non-value added. Okay, the engineer should define the problem, select the best suitable mesh and the best suitable solver and solver settings, and then should let the computer do all the automatic meshing, simulation, post-processing, and then he should sit down and look at the data and make the engineering call and the engineering judgment. That's what I mean with automation. Let the computer do the stuff. That's much faster, and it drives standardization and quality. Because in big companies like Rolls-Royce, we have workforce all over the place, and if we would let everybody do the meshing and simulation himself, then believe me, two people sitting next to each other, same problem, would come up with two different answers. So we need to standardize, we need to automate using the best practices. Okay. So, which one is the most important one? Obviously, there is no single most important one. All four need to work together to create the most efficient simulation. So, interesting question. If I would go to an engineer today and say, well, I'm going to give you a bigger computer, whatever, 48 cores and 512 gigabyte memory, what would you do? What would you do? Probably 80% of the people would say, I would put more mesh points in. Yeah, okay, which is fine, but it's only one thing that you can do. We see simulation as an enabler to do things that we were not able to do previously, or to do things more than previously. One is design space exploration. Okay, so again, in order to come up with a product which is good quality and we avoid any rework, because rework is usually the thing that causes all the time delay, we need to make sure that the decision that we made early in the design process about the architecture of the product, number of stages and things are the right ones. We don't want to go 12 months, 18 months down the line and then find out, oh, we need to change something in the architecture, because this is going to produce a lot of rework. So design space exploration is very important for us. Also to make sure that we have the best trade-off between different product attributes, which might be cost, weight, efficiency, etc., and also to de-risk the project. Yeah. That's one thing you can do. The second one is, coming back to the more mesh points, potentially, is to prove your design understanding, to use better physical models, or use even less models, and try to do large eddy simulation, direct numerical simulations, and things like that. So more detailed simulations. The third one we really do quite a lot in the company is nowadays more multiphysics. Okay, rather than just designing the product aerodynamically and then pass it to the stress engineer who does stress and then pass it on to the vibration engineer and etc., we try to do that together as much as possible on a single component level as well as on a subsystem level. So if you have multiple components, or even in some areas even on a bigger scale. And that's again to find the best trade-offs, to reduce the number of iterations you have between the engineering departments and the engineers, and that's really that's really accelerating the process. The last thing is the virtual product. Obviously, at the end of the day, when you design a whole product, you usually chop it off into smaller parts, subsystem systems or components, and then a whole bunch of people are working on it, and then you need to bring it back, and you need to make sure that the entire product works properly, and that's what we call virtual product. That goes into the area of the digital twin. Okay, those are the enablers for simulation. So where we are today, that's purely Rolls-Royce perspective. We obviously do a lot of computational fluid dynamics, to design the flow in our product. We do a lot of thermal modeling to understand the temperatures in our structures. We do mechanical simulations to investigate stresses, clearances, component movements. We do a lot of lifing of we call them critical parts. So parts which are heavily under duty, which are driving our shop visits. So how often our product needs to be maintained and stripped, parts replaced. There are critical parts which are heavily, which we need to design for life. We do structural, so deflections here, vibration. We do materials and process modeling, to understand basically the manufacturing process. We do a lot of cost simulation, basically to understand how much a component costs, how much the life cycle cost and unit cost of a certain component. We do manufacturing and assembly simulations to simulate the assembly process, the manufacturing process. We simulate the design process itself, so the different steps that an engineer needs to go through when he or she design a product. We simulate that, we capture the knowledge, we put it into a computer program, we simulate that in order to understand the value stream, to understand how we can accelerate the design process, which design steps can be done in parallel rather than in a sequent way, and obviously a combination of all of those. Just give you some examples. In different areas of the engine, we apply different type of CFD simulations, whether it's the traditional Reynolds average Navier-Stokes or LES in the combustion flow. We do a lot of cooling and cooled components, noise simulation, installation aerodynamics, so how the product is mounted on the wing or at the fuselage. That's on the CFD part. On the thermal mechanical part, we do obviously a lot of detailed component models, whole engine models, whether 2D, 3D, or also very detailed combination of components in order to understand contact, friction, lifing, etc. So what might be the future? I think just 2 slides left. I think that's the future. Actually, that's the history, because that's a picture I took a few years ago. That's in Scotland when I was on a leave. But can you imagine why I brought that up? What do you see there? You see a lake, you see some mountains, and you see the sky with hopefully some clouds. Cloud is a key word here. Okay, so I think the future is going to be cloud computing. The engineer should not care where he runs the code, his simulation. He should submit the simulation, and it should go off, whether it's a local computer under his desk, on a HPC, on a cloud, doesn't matter, whether it's Amazon or Microsoft, whatever. He should simply specify, this is the time. Let's say I need my results back on Monday morning, because on Monday afternoon I have a review, a technical review, and the system should then automatically choose the most efficient compute resource and probably the most cheapest computing resource, going to an Amazon cloud overnight when no one is ordering stuff on Amazon, whatever. Okay, so data lake, this goes to big data. We produce a lot of data. We have no time to look into the data properly. We don't spend enough time to do that, and that's basically engineering sits in the middle. Okay, but that was very simplistic. Okay, so computers are going to be cheaper and faster. Obviously, we will be more connected, not just between the computers, between companies or sites, but also between the manufacturing part, the service part, and the engineering part. More mobility of resources. Yeah, so we as a company, we are shipping out work packages, we call that work packages, small design tasks, to different locations. We need to make sure that our workforce in India creates the same quality results than our workforce in the States or in the UK, in Germany, and in Norway. Okay, more multidisciplinary, more multiphysics. The world is multiphysics, so we need to start doing multiphysics, okay, and even more. And more automation, and I think that's going to lead to better simulations overall. And that was my talk. Thank you very much.